So the shuffle card example shows you the idea of Markov chain Monte Carlo technique. And when we translate it into the language of model parameters, so say you have an unknown parameter theta that you're trying to calculate posterior of, and what MCMC will do, it will just generate a sequence of values. We're going to call it theta superindex G, with G going from 1 to capital G, whose stationary distribution, and so stationary distribution of this Markov chain, so each of those theta superscript G is an element of the Markov chain. So stationary distribution of this Markov chain is the posterior distribution P of theta given the data, something that we're trying to estimate. And then once you have the sequence, then you can do the calculations that you want using the sample. So essentially generate a sample from the posterior distribution. So for example, a typical thing that you want to calculate or estimate, you want to calculate an estimated an expected value of some function of theta given the data. Right, so in this case, it's just going to be 1 over G, and then you take an average. So f of theta, and you take elements of the sequence. G goes from 1 to capital G. And of course, this is just an approximation to the integral of f of theta given the p theta. This is our posterior given data. And then you have to integrate theta out, which is the exact value of the expectation of this function f of theta given the data. All right. So, and Monte Carlo technique has been around for quite a while. They've been first applied to understand physical systems, and they were used as part of the Manhattan Project. And you'll hear the name Metropolis and Hastings. Both of them were involved in the Manhattan Project. And in physics, you basically have these high-dimensional integrals that pop up, and they use those Monte Carlo simulations to estimate those integrals. And but lately, so statistics is another applications of those type of techniques, and optimization techniques, stochastic optimization techniques would be based on the Monte Carlo techniques as well in the optimization world. So this is estimating theta is the statistics example. In the world of optimization, you usually want to generate a uniform sample from some subspace, or from space defined by sequence of equations. So you want to generate a uniform sample, and the boundary is defined by equations, by constraints. So essentially, you have a constraint optimization problem. You have a sequence of constraints. Sequence of constraints has a geometric interpretation. They will correspond to certain geometry in the space. And then what you want to do, you want to uniformly sample from this geometry. So uniformly simulate points from the constraint space. So Monte Carlo technique will be used in these applications as well. But let's go back to statistics, and we're going to talk about the Metropolis Hastings algorithm. So we'll start by talking about the problem of identifying stationary distribution on a graph, on a random walk on a graph. So you have a graph that is given by the set of vertices and the set of edges. So set of vertices here is 1 through 6. And then the set of edges is all the edges that connect different vertices on the graph. So here's the graphical representation of this graph. And you have a transition probability from each vertex to each vertex. So each of those edges will have a transition probability associated with this. And we encode those transition probabilities in the transition matrix. And so, for example, here, probability of going from edge 1 to edge 2 is 1/2. So it's 1/2 going here, and then from edge 1 to edge 3 is also 1/2. So those are the probabilities. And essentially what we're interested in, let's say you have a random walk on the graph. So you start at some random edge, and at some random vertex, and then you transition to neighbor vertex according to the probability. So you roll a dice. So in case, let's say we start at 1, and then you roll a dice, or in this case it's just a coin with 2 sides, and with probability 1/2 you go to the vertex 3, and with probability 1/2 you go to the vertex 2. And then what we're interested in finding stationary probability. Essentially, you can think of stationary probability in the following way. If I do this random walk for a very long time, infinite time, then on average, what proportion of the time I will spend at each of the vertices. And essentially, every time I do a random walk, I spend a fixed amount of time, the same amount of time every single time I do on each of the vertices. So I spend 1 second, then move, 1 second, then move, then 1 second, then move. And then the goal is to understand this proportion of time I spend in each of the at each of the vertices. So this is called stationary distribution for the random walk. And in this specific example, the station distribution will have this following form. Let's say this is the parameter theta that we're trying to estimate, the stationary distribution. And in this case, actually, if you look at this matrix carefully, you'll see that we have 2 ones here, 1 here and 1 here. So those corresponds to the nodes 6 and 7. So this is transition probability from 6 to 7 is 1, and from 7 to 6 is 1. So which means with probability 1 from 7 you'll go to 6, and with probability 1 from 6 you will go to 7. And in this case, intuitively, it's quite clear. So the moment you get to 7 or 6, and we see that you can go to 7 from 3. Yeah, so there's 1/3 probability of going from 3 to 7. So at some point we will get to 7, and once you get to this vertex 7, you basically stay there forever in this 6-7 cycle. You go from 7 to 6, from 6 to 7, and so if you look at the infinite time and you look at the proportion of the time, then everything else before coming to 7 becomes irrelevant. It becomes small, and so the only thing that you do is switch in between 7 and 6. So half of the time you'll spend in the 7, and half of the time you'll spend in 6. So this is the stationary distribution for this specific random walk on this specific graph, and this is degenerate, so that's not usually if you work with applied problem, you're trying to avoid those type of degenerate distributions, and there are a whole bunch of techniques that deal with degeneracy. And the problem of finding stationary distribution is essentially a problem behind Google's page rank. This is how the pages would be ranked. In the case of the internet, you don't have 6 vertices, you have billions of vertices, and the edge between each of those vertices correspond to the link from one web page to another web page. So if there's a URL hyperlink, then there's going to be an edge connecting those 2 web pages. And essentially, Google PageRank tells you if you do a random walk on the internet graph, what are the pages you're most likely going to spend your time on, and those pages will be higher ranked in the search results compared to the pages with a low rank. And we actually can find the station distribution quite easily. And the station distribution, if you take the transition matrix, and actually in this transition matrix we say transition from vertex J. So Pij is the probability of transition from J to I. So we actually flip it, so we avoid the transposition every single time in our formulas. And the nice thing about finding the stationary distribution is essentially you start with some initial guess, theta 0, about your station distribution, and then you do what is called power iteration. So the next iterate, k plus 1, is just this transition matrix times theta k. And if you do it until you basically have what is called stagnation, so your thetas stop changing, then you find the stationary distribution. And you actually can say some nice mathematical properties about the convergence rate. In this case, the absolute value of theta k minus theta hat. So theta hat is the true value of the station distribution. The difference between those two in the 2 norm is going to be bounded by the absolute value of lambda 2 power k. And this one is the second largest eigenvalue of P.